Hi, everyone. This is the last lecture for Chapter 7, and we're going to be talking about energy in chemical reactions. Now, before we talk about the energy, let's talk about chemical reactions at the molecular level. In order for two chemicals to react, they have to collide with each other, and that collision has to have sometimes the right orientation. Maybe they have to be facing each other a certain way when they collide. And they have to collide with enough energy. If they have not enough energy, they might just bounce off. But if they have enough energy, then they can stick together or rearrange their bonds. So you need the two reactants to collide. They have to have the right orientation, and they have to have enough energy in that collision. And that energy in the initial collision is known as the energy of activation. And so we can draw what's called an energy diagram here. The y-axis is energy. The x-axis is the progress of the reaction. And so on the left side here, we have the energy of the reactants. And on the right side here, we have the energy of the products. And so in an exothermic reaction, heat is released, or it's a product. So here's an example. Carbon reacting with hydrogen to create methane gives off 18 kilocalories of energy. And so this distance here from the starting energy of the reactants to the energy of the products is 18 kilocalories. But it takes a little bit of energy to get the reaction started. And that little bit of energy here is the activation energy. That's that initial collision. It takes a little bit of energy to get the reaction going, and then it releases a lot of energy when the product is formed. You can kind of think of this as like gasoline in your car engine, right? When you burn gasoline, it gives off a ton of energy, enough energy to drive your car down the freeway. But gasoline doesn't just catch on fire on its own. That's why we have spark plugs in your engine. And the spark plug gives the gasoline that little boost of energy to start the reaction, which then releases energy. So you always need a little bit of activation energy for a chemical reaction, and then it's all downhill from there. And so this is an exothermic where heat is released. You can also have an endothermic reaction in which heat is absorbed, or it's a reactant. And so an example here is nitrogen gas and oxygen gas producing nitrogen monoxide. This is a non-spontaneous reaction. If you want to make this happen, you have to put energy in. So energy is on the reactant side. So if you look at this energy diagram, the energy of the reactants is lower than the energy of the products, meaning the reactants are more stable. And so in order to make this reaction happen, you have a huge activation energy barrier and then a little downhill. So endothermic has energy being absorbed, or it's a reactant. Exothermic has heat released as a product. So exothermic reactions give off heat, they feel hot. Endothermic reactions absorb heat, they feel cold to the touch because they're absorbing heat. All right, let's do a quick study check. Identify each reaction as exothermic or endothermic. And so this first one here, we see that the heat is on the products side. So this one would be exothermic. The second one here, the heat is on the reactant side. And so this is going to be endothermic. And the last one, heat is on the product side. And so that's going to be exothermic as well. Next thing we're going to talk about is reaction rate. When we say reaction rate, we mean how fast is the reaction occurring. some chemical reactions are really, really slow, right? Like, how long does it take for a metal tool to rust, right? It gets rained on, it doesn't rust overnight. You know, maybe if it gets left outside for weeks or months, then you start to see the rust. So that would be a slow reaction rate. A fast reaction rate would be like setting something on fire, right? That reaction is happening really, really quick. And so we can define reaction rate as the speed at which reactants are used up or the speed at which the product is formed. Reaction rate is proportional to temperature. So higher temperature, reaction happens faster. Reaction rate is also proportional to the concentration of reactants. So if you have, you know, only a few molecules flying around, they're not going to bump into each other very often. But if you have a ton of molecules flying around, they're going to make a bunch of collisions. And so if you have more reactants, it's going to react faster. So if you increase the concentration of reactants, you're going to have more collisions, faster reaction. If you increase temperature, that means the individual molecules are moving faster. And so they're going to collide more frequently because they're moving faster. So that'll also speed up the reaction. Now, the third way to speed up a reaction rate is to add a catalyst. Now, a catalyst, this is a new term, is something that's added to a reaction to make it go quicker, but it's not a reactant or product. As a silly example, let's say the chemical reaction is like dating, right? The catalyst would be like Tinder, right? Tinder is not part of your relationship, but it helps people meet easier, right? It's a catalyst to help people get together. Okay? So in chemistry, catalysts aren't part of the reaction, but it's just something that helps the molecules react quicker and more easily. And they lower the energy of activation. So if you look at an energy diagram for a reaction with a catalyst, here in purple is with a catalyst and blue is without a catalyst. And so normally you have this high energy of activation, but then when you have a catalyst, it's a low energy of activation. Now, the total change in energy between reactants and products is the same for both. It's only that initial boost that's different, right? So catalysts lower the energy of activation to make a reaction happen more easily. Okay, study check. Let's state the effect of each thing on the rate of a reaction. We're going to decide if each of these items increases, decreases, or has no effect on the reaction rate. So if we increase the temperature, that's going to make the reaction go faster. If we remove some reactants, so if you have less reactants going around, you're going to have less collisions. That's going to make your reaction slower. If you add a catalyst, catalysts make reactions faster. What if you place the reaction flask on ice? Well, that would make it cold. So if you lower the temperature, that's going to slow your reaction down. Now, if you increase the concentration of reactants, so if you have more molecules, you're going to have more collisions, that's going to be faster. Now, let's take a look at these things here. If we raise the temperature of this reaction, is it going to make it go faster or slower or have no change? Well, raising the temperature, definitely going to make it faster, right? What if we add more oxygen? Well, oxygen is a reactant, so if you have more of this, it's going to react faster. What if you add a catalyst? Well, adding a catalyst always makes a reaction faster. And if we lower the temperature, make something colder, that makes things move slower. It's going to be a slower reaction. Increase, 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 decrease. Okay, so that's it for this lecture video. Just remember the 3 ways to speed up a reaction is increase concentration, increase temperature, or add a catalyst. 3 ways to speed up a chemical reaction. An endothermic reaction is one that requires energy. Exothermic is a reaction that gives off energy. All right, thanks for watching, and I will see you guys in lab next week.